Hello, Farouk here, and I'm the lead instructor and tutor at DirectHUB.net. So every year, I help hundreds of students pass their FE exam. And we do this by developing the right mindset, building the right skills, and also testing our skills and practicing by applying the right resources. Okay, so I thought it would be fun to do this quick question covering the direct shear test. So this one's quite simple, and it's one of those we want to absolutely make sure we get right on the actual FE exam. So let's make sure we know how to do this, get it right, especially for these calculation type questions that don't involve too much of the concept or thinking about the concept. So this question is a calculation based question that strictly relies on the equations. So let's make sure we get it right. So we'll briefly talk about the concept, especially for direct shear test. And let's do that real quick right now. So if we look at our notes here, the direct shear test is just another lab test we do in the geotechnical field. So it's a geotech lab test. So the direct shear test, by definition, or also called the box shear test, is used to determine the shear strength of soil. So remember, soil gains its strength, as we call it the shear strength. Because if you can imagine compressing soil, it has no strength in compression. And if you pull it in tension, it has no strength in tension. But what we focus on is the shear strength, right? The shear strength for that soil. And that's what we mainly focus on for soil, shear strength. That's where it gets its strength. So then we know that the direct shear test specifically is more suitable to cohesionless soils. So if they were to ask you on the FE conceptual question, is it cohesion? Would you apply it for soil with cohesion? Or is it cohesionless soils? Just pick cohesionless, especially for the direct shear test. So specifically, these cohesionless soils are going to be granular soil types. So granular meaning it can be gravel, sand, silt, or coarse-grained soil with very little or no clay content. Also, I want to say you can do it for clay, but it has to be like a stiff clay type material. So often, most of the times, we do not use it for clay. We want to focus on using it for cohesionless soils, soils with no cohesion. And remember, clay it has cohesion, right? So we want to focus on for cohesionless soils, direct shear test. So we know granular soil has no cohesive strength. It has no cohesion. So then we know that shear strength is needed for engineering situations. We know we need that for determining the stability of slopes and cuts, finding the bearing capacity for foundations, and calculating the pressure exerted by the soil on a retaining wall, or in general, whenever the structure is dependent on the soil shearing resistance. So it's a very important property, and also the parameters we get when doing this test will be important. So now, if we look at the test procedure, let's look at what we have going on for this direct shear test. So what I'm looking at first is a cross section. We're looking at a cross sectional view. And let me point out the soil sample. So this is our sandy soil sample. So note, this is a cross section, and this thing is going to be cylindrical in shape. So it has a cross sectional area that we load of a circle, and it's going to be a cylinder. That's what we're looking at for the soil sample. So then we have a steel ball here. We have a pressure plate on top. So this is our pressure plate. And we have two porous plates. We have one on top and we have one on bottom here. And then the first step that we do is apply a vertical load to the specimen and wait for consolidation. So we're going to apply a load P and we're going to wait for consolidation, a vertical load P, and wait for consolidation. So remember, consolidation is what? Consolidation, essentially when we load something, it's the removal or expulsion of water from the voids, from the void space. So what leaves in consolidation is water. So it's the expulsion of water, then we have consolidation. Whereas compaction, it's the expulsion of air from the voids. So compaction, it's air that leaves the voids. Consolidation, it's water that leaves the voids. So just know that difference there. So then we know for step 2, the lower box is subjected to our horizontal displacement at a constant rate. So what we do is apply this force here in red at a horizontal displacement at a constant rate for step 2. And that's essentially the entire procedure of this direct shear test. So now if we look at an after image, we know that the testing procedure is going to look at essentially the same thing. And what we have here is the after condition where we have some failure. So we record, in this case, we have like an instrument here that measures the shear force, and we can also record that force P, the vertical load, when we do this test. So now, using these parameters that we record, what we can do is actually apply some equations. So these equations are provided in our FE Handbook on this page, the latest FE Handbook, and we can get the total normal stress. So it's going to be sigma n, and we just take the load divided by the area. So remember that it's going to be the cross-sectional area where the force acts. So it's going to be a circle, right? Picture a cylinder. That's going to be where the force acts. So then this is not applicable. It's on the same page, but this will not be applicable. But what is applicable is actually this, the shear stress. We can find that by doing the T, which is the shearing force. So that's the shear force divided by the area. And it's going to be the same area because that force is going to be applied to that same area, essentially that circular cross section. So that's the shear stress. And we can also get the shear stress at failure by applying this equation. And this shear stress at failure is in fact the most important because it comes from the Moore-Coulomb failure envelope, which is also discussed in our FE Handbook. So shear stress essentially is going to depend on the cohesion there and the angle of internal friction and the normal force. And if we look at a graph here similar to what we have of the Moore-Coulomb failure envelope, we know that the shear at failure, or the shear resistance, is going to depend on two components. It's going to depend on the frictional component, which is going to be this part, and it also depends on the cohesive component, which is that part. And what we do from this direct shear test is actually plot this envelope by doing multiple of these shear tests. So what that means is we do, let's say, 3 tests. We can plot, let's say, tau at failure here. Let's say call it tau 1. Then we plot sigma 1. Then we do the same thing. We get another one. This is tau 2, the shear. Remember, this axis is going to be shear, sigma 2. And we plot another one. And we get 2 respective points, tau 3. And we get the sigma 3. And with those points, we can collect them by straight line. And we can get that Moore-Coulomb failure envelope. And that's generally the steps we take. And from that envelope, we can get important soil properties, such as the internal friction angle. But now that's going to be the overall idea of the direct shear test. Let's actually solve this question. Okay, we're told a direct shear test was performed on a sand sample. So be careful, it's a sand sample. The sample has a diameter and height of 4 inches and 1.5 inches respectively. So when you're reading this, the diameter is 4 inches, that's what comes first, and the height is 1.5 inches respectively. So the normal load at failure is 200 pounds. The angle of internal friction is 38.48 degrees. The shear load in pounds at failure is most nearly what? So what's the goal? We want to find the shear load. So remember, shear load, if we use the FE Handbook, is it this or is it this? Shear load is a force. Shear load is the same thing as shear force. So it's just T. So that's going to be the force in pounds. And that's what we want to find. It's just capital T. It's not tau. Tau is always shear stress. So that's the goal. We want to find that in units of pounds. So now let's denote what we're given. We're given a few things here. So we know we're working with a sandy sample. It's sand. Also, we have a diameter. So this is essentially a cross-section of a cylinder of the specimen. And it has a diameter here. What's that diameter? The diameter is going to be 4 inches. That's given. So we know also it has a height, which is also given, of 1.5 inches. So we have that. Then we know that the load at failure, so we know when we do this test, we talked about it in the lesson down there, is we have a load at failure. And it's going to be a normal load. And they specifically say that in the problem statement. So it's a normal load at failure. So we're going to call that load P for the load at failure. So that's going to be 200 pounds. Then we know the angle of internal friction. What do we denote that as? It's always phi. In geotech, it's always phi for the angle of internal friction. So it's going to be 38.48 degrees. Let's dive into that solution now. So for the solution, we know the end goal again is to find the T, the shear force or the shear load at failure. So let's go into our equations. How would we do that? So we know, okay, we have an equation for shear stress. Shear stress, let me denote that here, is T, the shear force over the area. So we want to find T. So we can rearrange this. T is the shear force. It's going to be the shear stress times the area. And that's actually the equation we're going to apply at the very end. That's how we get the shear force, the shear load. So then we know that this tau is the shear stress at failure in this case, when the soil fails. So the shear stress, how would we get this? How would you get this one? Applying this, right? It's the shear stress. We can actually take this and put it in there. So we need to get this. And the way we can get this is by solving this equation, the right side of the equal sign. We need to solve this equation, and we can actually get this by doing what? By going all the way above. So we can go here and apply this equation, right? So what we need essentially is going to be finding, so the steps involve finding this first, then taking this, plugging it in here, then finding the shear stress, then plugging it in the shear stress and solving for the shear force. And that's what we'll do. So let's do that together. And I want you to do it with me. You can pause the video and attempt it. So now we know step one, we will find that the load, the normal load at failure. It's the normal stress at failure. So let's see, find sigma n at failure. So sigma n, remember, is a normal stress at failure. So sigma n is what we find as the first step. What we do is P over A. This is down there in the FE Handbook. So now what's the load P? P we found, it's going to be actually given, right? 200. That's given in the problem statement. So we take 200 pounds. So now what is the area? So remember, in this case, we're loading a cylindrical specimen. And the biggest hint, it's a diameter. It has the word diameter. So it's going to be the area of a circle, right? Diameter relates to the cross-sectional area of a circle. We're loading this cross-sectional area, and it's going to be a circle. So the area of a circle with respect to diameter is pi d, the diameter, which is going to be 4 inches in this case, squared over 4. And that's what you get for that. So now, sigma n, if you solve for that, let me see what I got. So I got a value about 15.92 psi. 15.92 psi. So psi simply means pound per square inches, right? And that's what we got in our pound per inches squared. So that looks right. So now let's keep going. Step two. Step two, we said down there, is to do what next? Find the shear stress at failure. So we will find, let's call it find tau F. This is shear stress at failure. So step two. So now tau F, let's do that down there. Tau F is going to be given by the equation in the FE Handbook. So we know it's going to be the cohesion plus sigma n. Then we take tan of the angle, internal angle of friction, angle of internal friction. So we already know this, right? This we found. Phi is actually given in the problem statement, 38.48. C is what? What is C in this case? It's 0, right? C is 0 because you're dealing with sand. We said sand always has a cohesion of 0. So sand is cohesionless. So if you have clay, it has cohesion, so it will have a specific cohesion value. But for cohesionless soils, sand, gravel, those types of soil, granular type soils, it's going to be cohesionless, so it has the cohesion C is 0. So that's what we put for C. So tau F is going to be 0 plus, so sigma n we found it's going to be the 15.92 psi, pound per square inches. Then we do tan of the angle, so the angle is going to be 38.48 degrees. Okay, so that looks good. Tau F, it's going to equal to, let's see, I got 12.65 psi. So PSI is pound per square inches. So it's still the same units, but it's going to be a shear stress, right? Shear, which is like along the plane. So now that's the shear stress at failure. The last step is to find the shear force. So find shear load or force. Shear load, which is the same thing as force, and that's going to be capital T. So for that, T is going to equal what? We set it down there. The shear force is going to be the shear stress times the area. It's still the same cross-sectional area that's being loaded. In this case, it's going to be in shear. So we know this tau is going to be tau F at failure. So that's what we do for that one. So we do the 12. So let me actually denote that. It's going to be tau F times the area. So we do the shear load at failure. We have 12.65 psi, pound per square inches. Let me actually write that, pound per inches squared for psi. Then you multiply by the area. It's still the same area, so it's pi d. D we know is 4 inches, the diameter, squared over 4. That's the area of the cross section. So now for the shear force, we get a value of about 158, 159 pounds. And if we look at our answer choices, the closest one, which is often on the FE, you'll see stuff like this. The one that makes the most sense has to be 160, right? It has to be that 160. So this would be about 160 pounds. And that's going to be the shear load or the shear force at failure. So it should be C for that one. So I hope you found this practice question helpful. And I know for me, this was definitely a fun one to make and actually go through, especially because it's a calculation-based question. So it's a calculation-based question where we're using equations, relating different equations, and ultimately doing our computation to get that final answer. But I want to note that on the FE, we will get tested on the concepts. So I tried to briefly talk about the concept behind the direct shear test, what it entails, the overall idea of the test, because the FE will probably test us on the type of test, when is this test applicable, and so on. So we have to know the concept, and we have to know these type plug and chug equation type questions as well. And I want to say these are probably on the easy side, these type of plug and chug. So we want to make sure we get them right, especially with correct application of the equations, relating equations, because these are probably the ones on the easy side, the computational type, plug and chug type questions. In my Civil FE review course, we cover hundreds of practice questions similar to this, and also ones that are conceptual. So we're going to cover conceptual questions, conceptual practice questions, and also computational type questions similar to this, by most importantly applying the FE Handbook. So we do both and get a lot of practice in. And the overall idea of this course, of the platform, the DirectHUB platform, and what we have as resources is to help you build your mindset. So build the right mindset before taking the FE exam, because that mindset is what you have with you throughout the whole time, throughout your studying and on exam day. So with that mindset, you will develop the right study habits, build the right study structure, have the right motivation, and regain and rebuild your confidence before taking your FE exam. Then from the mindset, this relates to applying the right skills or learning the right skills. So the right skills may involve the application of the calculator, or looking at a problem statement and looking at what to find and what's actually being asked. What's the goal of the problem statement? What are we given? And what is unnecessary information? Are they trying to trick us? In fact, this one, there is something that's extra we didn't use. So I'll leave that up to you to look at what that was in this particular practice problem. Then at the end of the day, we want to test our understanding by applying the right resources or applying the right practice questions that are relevant and updated to the FE exam. So these are practice questions that cover concepts, computation, and also ones that are very similar to the FE exam style type questions. So if you're looking for something like that, and if you're looking for a full in-depth review course where you have the only resource you will ever need to pass your FE exam, just check out the link in the description below. And I thank you for your practice. Have a good day.